Hello and welcome to topic 4, multivaluedness and branches. In the first topic, we saw that the argument of a complex number is only defined up to terms in 2 pi I. And for some complex functions, this ambiguity in the input leads to multiple output values. In this topic, we will see that we can cut the complex plane to restrict the function's input. And this defines a single valued branch where the function is analytic. In this first video, we're going to look at why some complex functions are multivalued. After watching this video, you should be able to explain the multivaluedness of the complex logarithm function, and you should also be able to use the multivalued complex logarithm to identify multivaluedness of powers of complex numbers. And let's begin.
Let's begin by talking about multivaluedness. First of all, what is it? Well, we often encounter many to one real functions. These are functions that give the same output for multiple input values. And an example that we're all very familiar with is something like the sine function. Say f of x is sine of x. And we know that this is a real function, and for now we're considering real inputs. We can depict the inputs on the real number line. And let's mark a few values of interest. So we might have minus 2 pi, minus pi, 0, pi, and 2 pi. And this is the values of x, which are the domain of the function, or the input. The output can also be depicted as a real number line. We have sine of x. This is the range of the function, which we understand to mean its output. And we know that all of these values of x, when plugged into sine, return 0. So we can draw this as a mapping of multiple input values to the same output value of 0. Of course, this is probably clearer if we draw the sine function on some axes. We have x, we have sine x, and obviously we have that the function looks like this, where we have 0, pi by 2, pi, 3 pi by 2, and 2 pi. So we can see that there are multiple points where this function, and of course it carries on each side, there are multiple points where this function crosses the x-axis. There are multiple inputs to the function that give a y value of 0. So it crosses the x-axis multiple times. The inverse of such a function is 1 to many. In other words, multivalued. And this is clear from what we've written above, that multiple input values can give rise to the same output. So the inverse function would take that output and map it to multiple starting values. So again, we can draw a picture to make this a bit clearer. Here again, we have the input to our function x. And now the function we're interested in is arc sine of x. Now the value of interest here is 0. And of course we know that given this input, we can get multiple output values. So essentially this is a reflection of what we have at the top of the page. And this time we have this kind of structure. Once again, this is also clear if we plot it on a graph. This is x and arcsine of x on the y-axis. And it looks something like this. Where, for example, here is x equals 1, here is x equals 0, and of course we have pi by 2. These are the values on the y-axis, minus pi by 2, minus pi, minus 3 pi by 2. We see that an input to the inverse function arcsine of x, such as x equals 0 or x equals 1, can give rise to multiple output values. To make this concrete, I'll just write down that if we have the arcsine of 1, then we know that that gives multiple values like pi by 2, 5 pi by 2, 9 pi by 2, and so on. And the question here is which value should be used. Well, for real functions, to solve this ambiguity, we usually limit the output to some fixed range. For example, in this case, we would insist that the arcsine of x lies between minus pi by 2 and pi by 2. And so looking at this plot on the right-hand side, that would make the function 1-to-1. There would no longer be this ambiguity. Once we've done this, we say that this then defines the principal valued arcsine function. Things get more interesting when we extend this discussion to complex functions. So the next heading is principal values of complex functions. As we saw in our discussions towards the end of topic 1, when we looked at complex roots, this overparameterization of angles that we saw in the example above, so it's true for sine, it's also true for cosine, this overparameterization of angles makes complex functions multivalued. In topic 1, we looked at the example of the nth root of a complex number, and we saw that the overparameterization of the argument of a complex number means that there are multiple roots for a complex number. To make our discussion more concrete, let's consider a complex function. So let's write some complex function f of z. Now let's write the output of this complex function as a complex number w, and let's write that complex number in modulus argument form. Now of course we know that complex numbers have arguments only defined up to multiples of 2 pi, so we're free to rewrite this as phi plus 2n pi as the argument, where n is an integer. Oops. and that won't change the complex number w. Now, finding the inverse function that takes w as input can give an answer z that depends on n. In other words, the inverse function of this function as written will be multivalued. It turns out that similarly to real functions, and we will discuss this further in the rest of this topic, we can handle this by restricting angles in the complex plane to principal values. So in this case that we've written above, we might set n equal to 0, and that ensures that the argument of w lies between 0 and 2 pi. Let's now look at a concrete example. Let's consider the exponential function, the complex exponential function. And this function will return some complex number w. Now our task is to look for the inverse. So we know that eventually we'll be able to write this as something that looks like the logarithm of the complex number w. So we're looking for z in terms of w. Let's put down some notation for what's next. Let's write z as x plus iy, and w as above as r e to the I phi, where x, y, r and phi are real numbers with appropriate ranges. We now write down that our complex function, whose value is w, is given by e to the z, which we can write down as e to the x plus iy. And this next step I'm not going to show explicitly. You can convince yourselves by using the power series expansions of the exponential. We can break this up as e to the x times e to the iy. If we consider the modulus of the complex number w, then clearly from what we've written on the right-hand side, the modulus of e to the iy is 1, and so the modulus of w is given by simply e to the x. This means that we can invert this expression to write down that x is simply the logarithm of the absolute value of w, which is a real number. So this line here is unambiguous because the real logarithm, which maps a real input to a real output, is 1-to-1. We're trying to find z in terms of w, and the real part of z, given by x, is the real logarithm of the modulus of w. So that's unambiguous. But it turns out that the inverse for complex exponentiation is multivalued. Multivaluedness here comes from the imaginary part of e to the iy that we saw on the line earlier. We know that from Euler's formula, e to the iy gives us cos y plus I sine y. And of course, cos and sine are periodic. This means that values of y differing by 2n pi, where n is an integer, produce the same value of e to the z. Therefore, e to the z is periodic, and in particular it's periodic with period 2 pi I. So we can write e to the z is e to the z plus 2 pi I times n. We therefore see that multiple inputs to the complex exponential function give rise to the same output. Now, because e to the z is many to 1, then as in our discussion earlier of the sine function, we expect its inverse to have this multivaluedness issue. In other words, this overparameterization issue. We have that our complex number w is given by e to the z, and we want the inverse. We know that we also wrote w is r e to the I phi, which is the same as r e to the I phi plus 2n pi. This means that if we apply the inverse of complex exponentiation to both sides, we will have something like the complex logarithm of w is given by the complex logarithm of r e to the I phi plus 2n pi. I'll note here that I've capitalized the L of ln because this is going to be the multi-valued version of the function. And later on in the course I might be a bit sloppy with when I capitalize this letter or not, but whether it's multi-valued should be clear from the context, and we'll be looking at this later and in the example sheet. We apply the normal rules for the logarithm, so we can split up the logarithm of a product into the sum of logarithms. The logarithm of the modulus r, that's a real number, so we can write that as the real single-valued logarithm. And then the exponent is going to give us I, lots of phi plus 2n pi. This phi, we said, lies between 0 and 2 pi. And here it's the value of n that gives rise to multiple values of this complex logarithm. I'll note that n is an integer. Clearly from this bottom line, we see that the complex logarithm of w is infinitely multivalued, where those values are dictated by the parameter n. So I will note, hence the logarithm of w is an infinitely multivalued function of w. How do we fix this problem? How do we combat this ambiguity? Well, we define its principal value, so the principal value of the complex logarithm function. We denote this by a lowercase l for the ln, by taking n equals 0. And hence we have that the principal valued version of the complex logarithm ln w is given by the logarithm of the modulus of w plus I times its principal valued argument. We can now handle the multivaluedness of complex powers and exponentials generally using the usual rules for real logarithms. What do I mean by that? Well, let's take another example. Let's imagine that we're interested in taking some complex number z and raising it to the power of another complex number, w. Well, we know we can always rewrite something like this as e to the power of the complex logarithm of z to the w. Using our usual rules for real logarithms, we can bring the power of w down out the front and rewrite this as e to the w ln of z. Now, inserting z in modulus argument form will give us e to the w times the real logarithm of the modulus of z plus I times the argument of z, and then the multiple values to n pi, where n is an integer. And this means that, again, we can define the principal value of this complex function when n equals 0. A surprising example of this is if we let z and w both equal I. We're now interested in the value of I to the I. Let's use the expression that we derived above. We can rewrite this as e to the I, then the logarithm of the modulus of I, and then plus I times the argument of I plus 2n pi. We have e to the I, then the modulus of I is simply 1, and this returns the real logarithm of the number 1. The argument of I, its principal value is pi by 2, and then we have plus 2n pi. And we can tidy this up a little bit. So the ln of 1 is simply 0, because e to the 0 is 1. And hence we're left with e to the minus pi by 2, because the i's multiply together to give minus 1, e to the minus, and then pi by 2 plus 2n pi. Remarkably, this is a real number. So if you take the imaginary unit and raise it to the power I, you end up with a real number. And here the principal value, when we set n equal to 0, is e to the minus pi by 2. I will note here that z to the w is single valued if w is an integer. It is t valued if w is real and rational, specifically of the form s over t, where the fraction has been written in its lowest form. In other words, the number of values of z to the w is determined solely by the denominator of the rational number w in its lowest form. And finally, this function is infinitely multivalued otherwise. And we just saw an example of this where if w is a complex number, then z to the w has an infinite number of values parameterized by n. To finish this video, I'm quickly going to write out an example that we already saw in topic 1, but which hammers home what we just covered and what I've written in the line above. Suppose z is complex, but w is real and given by 1 over k, where k is a positive integer. Let's imagine we're after the kth root of z, so z to the 1 over k. Well, as before, we can write this as e to the 1 over k times the complex logarithm of z. Expanding this out, we have ln of the modulus of z plus I times its argument plus multiples of 2 pi. And we can bring down the modulus of z, noted r, and the argument is going to be theta plus 2n pi divided by k. Here it turns out that the only values of n that matter are 0, 1, 2, all the way up to k minus 1. And you can check yourselves that for other values of n, we recover roots already found. In other words, the take-home message of this last point is z has k distinct kth roots. And that's very important to bear in mind when dealing with complex numbers. And we're going to explore this point more in the next video for the case of k equals 2, looking at the square root. A quick recap of this video. We started out by defining what it means for a real function to be multivalued. We then saw how multivaluedness can arise for complex functions. We looked at the example of the complex logarithm, looking at its multivalued and then principal valued versions. And finally, we looked at a couple of concrete examples where multivaluedness arises for complex functions and how to define principal values. Up next is the second video of topic 4. Thanks for listening.